the part that is changing with temperature is the delta S by T part. So if you draw a graph of delta G, the difference of free energy, in function of the temperature, you will get, I'm not sharing at this moment. I'm just answering the question that was asked in the chat. So, but of course, I cannot project anything because I could not expect this question. But if you have a graph of delta G in function of a temperature, you get a line which can go up or can go down. And that depends on the value of delta S, the difference in entropy. So this is the slope of the reaction. So that means if your entropy change is positive, delta G is going down. The line of delta G is going down. If your delta S is negative, that means your delta G is going up, which is in fact unfavorable for your reaction. So I hope that would be an answer to that question. But I think we could get back to that, I think, in the recapitulation slides. So if there are no further questions, I could indeed now start sharing my screen. Yeah. And at that moment, it will not be possible to look at the chat at the same moment. Let's see. Yeah, recapitulation part 1. Okay. Yeah, I think I will try to maximize. Okay, I hope you now see my screen, and the first slide is recapitulation stoichiometry. Is that the case? You can speak up if you want. Can somebody say something?
Yes, we can see.
Okay, very good. So you see the screen, yes? So the first chapter on stoichiometry is a very small chapter, so I included only a little information. It's also not a very difficult chapter. So in the first slides of that chapter, I talked about what it means, stoichiometric mixture. So if you write a reaction with all the right coefficients, so that means the stoichiometric mixture would be a mixture in which the ratio between the reagents is exactly the same as the coefficients of the reaction. We will give some examples later on. Very often, the mixture of reagents is not stoichiometric. So that means there will be one reagent that is not used up after the reaction. It is the reagent in excess. And there will be another reagent which is completely used up. This is the limiting reagent. Then the ratio of the reagents is different than the stoichiometric ratio. And I think this is kind of evident, but it's good to know this because it's used in some exercises later on. Maybe a little bit more interesting to look at is I have to go back, the ideal gas law. You see it in the red. PV is nRT, in which P is the pressure, V is the volume, N is the amount of mole of gas, R is the gas constant. Now, this is interesting to consider because the gas constant actually can have several values, and it depends on what unit of pressure you are using. In most cases, the pressure is in atmosphere. and that's what you see in blue. Then you have to fill in R is 0.082 liter per atmosphere per Kelvin per mole. However, in thermodynamic calculations, your pressure is not in atmosphere, but in kilopascal. And in that case, it's another, these are other units and also another value. So in that case, R is 8.3 Joule per Kelvin per mole. So if you are doing exercises, it's important to consider whether you're working with atmosphere or you're working with thermodynamic calculations which use kilopascal, because otherwise you will make a mistake in your calculation. So let's do a small exercise. This exercise is based on a reaction of potassium with water. This results in a violent reaction, and there's a gas that is being formed. And so we will need for our calculations the gas law, the ideal gas law. So the gas formed is collected in a burette. That's a piece of glassware in which you can collect gases, and you can measure the gas volume. You can see that it has increased by 36.5 milliliter. And this was done at a temperature of 20 degrees Celsius. It's also done at pressure of 1 atmosphere, and the vapor pressure of water at 20 degrees is 0.023 atmosphere. Now, what does that tell us? That tells us that the gas doesn't consist only of hydrogen, because that's the gas that is formed, but there's also a partial pressure of water of 0.023. So what do we have to do? We have to calculate how many grams of potassium has reacted, and we have to calculate that back. That's a stoichiometric calculation based on the molecular weight of potassium and stuff like that. These are things, these data, like molecular weight, that you can find in tables. So, and in, for instance, the periodic system of elements normally also lists the molecular masses of the elements. It goes on, and it's as a second part of the question. So we take that gas mixture. So we have the gas that is formed, and we already know that this gas is hydrogen. We have excess of air, and air contains nitrogen and oxygen. So we bring it as an electric spark, and now there's a reaction between the hydrogen and the oxygen that is in the air. We should calculate how much of the gas volume will be decreased as a result of that second reaction. We bring back the temperature to 20 degrees because probably when hydrogen and oxygen is combining, it will release a lot of heat. So the temperature is increasing, but we bring it back to 20 degrees Celsius. So we stay at 1 atmosphere pressure. Okay. So now, of course, is how do we start with this? And the good start is always to write the reactions that are involved, because from the reactions, we can derive the stoichiometric coefficients. And this we need to initiate our calculation. So you can see the reaction over there. And it says that 2 atoms or 2 moles of potassium have to react with 2 moles of water to release 1 mole of dihydrogen. There's also potassium hydroxide formed, but that, of course, stays into the solution. So what we will measure is the hydrogen that is escaping. You see, the stoichiometry is 2 to 1. because we will calculate the amount of mole of dihydrogen, but that's not the same as the amount of mole of potassium, because that is the double. So how many moles of hydrogen did we form? For that, we need the PV-nRT formula. N is the amount of mole. And now we fill in everything we know from the given of the exercise. P, that's the partial pressure of the hydrogen. And so that means we actually have 1 atmosphere, but there's also water present. So we have to subtract the amount of water. 0.023. The volume was given as 36.5 milliliter. So we convert that to liter. That's this 0.0365. We also divide by R. It's an atmosphere calculation. So R is 0.082. And the temperature is in Kelvin. So 20 degrees Celsius means 293. So if you do all of that, we get 0.00148 mole of gas. So 1.48 millimole of gas, in other words. So from the formula, we see that to get that, we need a double amount of moles of potassium from the stoichiometric equation. And we know that potassium has per mole is 39.1 gram. And so if you calculate that, you just multiply. That means to get that kind of amount of dihydrogen, we need 116 milligram, so 0.116 gram of potassium. That's the first part of the question. Now, the second part is, okay, we have the hydrogen, we reacted with oxygen in the excess air. So the first is to make the right equation. So hydrogen is H2, oxygen is O2. We have water. Now, water at 20 degrees Celsius is a liquid, of course. So that means the other two are gases, hydrogen and oxygen. They disappear, these gases. You also can see it's a 2-to-1 stoichiometry. So only half of the amount of moles of hydrogen is used for the oxygen. So that means we had 36.5 milliliter formed dihydrogen. We need half of that, 18.25. I will go back, 18.25 milliliter of oxygen. So that means, as compared to the starting situation, so we generated 36.5 milliliter hydrogen, but we lost it again. But we also lost the oxygen, 18.25 milliliters. So in the total, we lost a volume of 18.25 milliliter after the two reactions. So as compared to the starting situation. So this is, I would say, a typical stoichiometric exercise. And I hope it explains a little bit what do we mean with a stoichiometric calculation. I have a second example on the next slides. So here we start from solid sodium azide. Sodium azide has a formula sodium N3, and this explodes upon thermal activation. You form sodium and dinitrogen. This is an interesting reaction, in fact, because that's what happens in an airbag. You know, you have airbags in your car. If you would have an accident, this blows up very fast. And that's, in fact, the dinitrogen that is forming. And this blows up a bag, and you, let's say, can cushion any kind of force as a result of the accident. But now here we do a calculation. So we want to calculate which kind of gas volume is produced as a result of the decomposition of 100 gram of sodium azide at room temperature, 20 degrees Celsius and 1 atmosphere. Interestingly, 100 gram sodium azide, that's about the azides, the amount of azides that you can find in a car, in an airbag. That's more or less the amount that you have there. Okay, we have to use again the ideal gas law, and we want to calculate, in this case, the volume. So if you rewrite it, that means V is nRT divided by the pressure. Now let's see what do we have as for the data that we need. We have the temperature at 293 converted from Celsius to Kelvin. We have R because we use atmosphere, it's 0.082. We have the pressure. In this case, it's only nitrogen, so the pressure is 1 atmosphere. What we don't have at the moment is the amount of mole of gas. So to know that, we know we have 100 gram, but we don't know, of course, how much mole of dinitrogen this is going to be. So we need, as always, to put the equation. And you can see that 2 moles of sodium azide give 3 moles of dinitrogen. So this is important to keep in mind. So it's a 2-3, or you could also say 1 mole gives 1.5 mole of dinitrogen. Now we know that the molecular weight of sodium azide is 65 gram per mole. So if you have 100 gram, that's 54 mole. So if you multiply that by 1.5, you get 2.31 mole of dinitrogen. So that's N. N is 2.31, yes. So you see, we fill it all in, and that means we get our bag is blowing up, and we get 55.5 liter of dinitrogen. Okay, good. That's what I wanted to say about stoichiometry. So the next chapter, I would say, probably much more important, is a chapter on thermodynamics. And we already had a question on that just now. The first very important points that I would like to recapitulate are the laws. We have 3 laws of thermodynamics. And in the first law of thermodynamics means that in an isolated system, there cannot be any change of the internal energy. So delta U is 0. It can be rephrased as the law of conservation of energy. So that means energy cannot be destroyed. So it's you can take energy away, but you have to compensate it. So it's like action and reaction, almost, you could say. So we also defined what is enthalpy. So enthalpy is in fact the internal energy U multiplied by the factor PV, and that's again pressure and volume. And that means it actually compares with the heat. Enthalpy, you can say, is more or less the same as heat. Maybe this is the reason why it has the capital H from heat. Normally, we cannot measure enthalpy, but we can measure differences of enthalpy, delta H. And so it then translates into delta U, difference in internal energy, plus P delta V. You can express that either in kilojoule or in kilojoule per mole, depending on what kind of process that you're talking about. When it's, for instance, the formation of 1 mole of a certain compound, or the melting of 1 mole of a compound, or the distillation of 1 mole of compound, it's kilojoule per mole. When you're describing a reaction, again, with the right stoichiometric coefficients, you will describe it in kilojoule. So the second part of that we discussed was the entropy. And entropy is a kind of measure for disorder. It's also dependent, it's in a time, sorry, not time, temperature dependent part of the free energy. So it's not in the unit Joule, but it's in Joule per Kelvin, because you have the term T delta S. So this is in Joule per Kelvin. Be careful if you do calculations, because enthalpy is in kilojoule and entropy is in Joule. And of course, the difference is a factor of 1,000. So take that into account when you do any thermodynamic calculation. The second law of thermodynamics is saying that the driving force of a spontaneous process is always going towards a more chaotic state. That means you go to more disorder. Or in other words, the total entropy has to be, the total entropy change has to be positive. So, and the third law of thermodynamics, which we don't use a lot, says that the entropy of a perfectly crystalline substance at 0 degrees Kelvin equals 0. This also means that temperatures of below 0 Kelvin are not possible, because by definition, at that point, everything stands still and you cannot go, let's say, under that threshold. So if you do a calculation and you see that you have a negative, temperature in Kelvin, for sure, you made a mistake. And then here we have the free energy, and this is a little bit an answer maybe to the question that was asked in the chat. So the free energy is in fact, yes.
Sir, can you go back to the last slide, please?
I would, to the previous slides. Okay,
Yes,
please, yeah.
Can you explain the driving force of the spontaneous process? Can you explore that a little more? What do you mean by driving force?
Yeah. I say it means the spontaneous direction. So the spontaneous direction is always to go to more chaos and not to go to less chaos. So for instance, if I think I hear some echo, maybe some people should close their microphones. So anyway, so for instance, there's still a lot of echo. So if you have a gas, it means the gas will always spread around in any volume to the maximum chaos. So it will not be on the left or on the right. That is a more ordered state. It will always go to the maximum chaos. Also, for instance, suppose you have a glass of water at 0 degrees and a glass of water at 100 degrees. If you mix them, the same volumes, you will arrive at something at 50 degrees. That's a more chaotic state than the two glasses which have a different temperature. It's not possible spontaneously to take that water of 50 degrees and to separate it into a glass of water of 0 and of 100 degrees. If you want to do that, you have to invest energy. That's not a spontaneous process. And so So you have processes that are easy. Those are normally the ones that go to more chaos. If you want to destroy chaos and make order, you need energy. So I hope that answers your question a little bit.
Yes, that explains a lot. Thank you. But I want to ask, like, why is that? Why is a spontaneous process from a less to a more active state, but not the other way around?
Okay, that is a more, I would say, philosophical question almost. So I think it just, I think order has a cost. Order costs energy. And I think you just always go to the position of the lowest possible energy. It's like water always flows to the lowest position. Water will never go up because that is against the logic, I would say, because that would cost energy rather than releasing energy. So in general, you always go to a place where you can be in the lowest possible energy state. And that corresponds to the more chaotic states. But I realize these are difficult concepts. But if you sometimes explain them with some practical examples, it actually makes a lot of sense. So you could say, okay, why does water not flow to the mountain, but from the mountain? Well, everybody understands that, I think, because that's what you would expect. That's according to the lowest energy. So it's something very similar to that. Okay, so I hope that helps a little bit. But there are difficult concepts.
Well, the idea that order takes energy, I think that's a key point. I love that. Thank you.
Yeah. Okay, good. Let's see, the free energy. So you see we have two terms, enthalpy and the entropy. To bring them to the same units, you multiply the entropy change with temperature. You can see indeed that the temperature dependent term is the one of T delta S. And a spontaneous process, and that's a little bit in the same vein as the question we just had. You go to the most negative free energy. So that means if your delta G is negative, that's a spontaneous process. And that's I would say, very similar to what we just discussed. So a delta G that is positive, you can compare with the river that is flowing upwards in the mountain. So that's not a spontaneous process. If you want your water to go up on the mountain, you will have to work. You will have to bring it up because it's not going to go spontaneously. So it is similar to that. For many processes, we discuss standard enthalpy, entropy, free energy. And that means your conditions are fixed. Often it's written as delta H with this small zero and so on. What does it mean? These are standard conditions. And standard conditions are when you have gases 1 atmosphere of pressure. When you have compounds that are in solution, the concentration is 1 molar. And also, all of the products should be at the most stable aggregation states at the temperature that you work. The temperature is not part of the standard conditions because the delta G is temperature because of that, the delta G is temperature dependent because this is a variable. Delta H and delta S are normally not temperature dependent, but of course T delta S is temperature dependent, obviously. So what we also discussed is that all of these thermodynamic state functions, these thermodynamic units are state functions, and that leads to Hess diagrams and thermodynamic calculations. And we can do a few of them. I think I will have some examples in the next recapitulation session. So what does it mean, a state function? This is another difficult concept. It means actually that a certain system, a chemical system, for instance, can be in a certain state, meaning it has a certain pressure, it has a certain temperature, it has a certain concentration of reagents or pressure of gases or something like that. It actually, this system doesn't know how it was getting to the state. In other words, the system has no memory of how it arrived. So, in other words, if you go from a state A to a state B, it doesn't matter what pathway that you are using. You could go via another state, C. You could go via another state C, or you could go first via D and then E and then still arrive at B. The energy of going from A to B is always going to be the same. It doesn't matter which pathway that you are following. And that leads to Hess diagrams in which you put all the intermediate states and in which you can then make calculations of the overall difference between A and B, or any difference between any of these other states. This may sound a little bit theoretical, I think, but we will see a number of examples of such calculations in the next recapitulation section. So I think for now, this was only a short recapitulation session. I think this was my final slides. And in the one of next week, we will discuss more points about thermodynamic calculations. So I don't know if you have any further questions at this point. I will close maybe I will stop sharing, I think. Yeah. Yeah. And I think I can then go out. I'm not so used to let's say screen sharing is paused. Stop share. Okay. Yeah. Okay, so in the meantime, I see that in the chat there was, is there any formula that could connect delta H, delta S, and delta G? I think we gave that formula in the presentation. So the formula is delta G is delta H minus T delta S. So you also need a temperature to connect these three units. So I think that question was explained. So I still have a few minutes. So if you have any further questions, please ask them in the chat and I will try to answer them. Yeah, the slides were already sent. So, and these slides, even I think I have them with pre-recorded also. So I think your teacher can make them available to you probably after the class. But the slides are certainly available. Yeah.
Sir, can you explain the gas constant, like the mechanism and how can we find that? Like the how and why of R.
Yes, the gas constant R is something that actually is found in many different formulas, including the gas law, and it's just a constant that connects pressure, volume, temperature, and the amount of moles. So and then the gas constants could have several values, but that actually depends on the units that you're using. So in most cases, when we do exercises with gases and we need to do stoichiometric calculations, it is given in atmosphere, and then you need 0.082 for the gas constant. In all the other cases, and we will see some examples of that in the next sessions, the R that you have in thermodynamic calculations is of a different value and is 8.3. So when that is that you have to take into account. There's a question about non-state functions. In thermodynamics, we don't discuss any non-state functions. So that's typically, and I think it's not really relevant for this course, but a non-state function would mean that it is important to know how you arrive at a certain at a certain position. So that's something that has memory. But I think in the context of a course of thermodynamics, we don't discuss let's say such non-state functions. But there might be a certain materials, for instance, in which it's important how something was prepared, to know what are the let's say what are the properties. So anything that has a memory has to be made according to non-state function. But let's not go too deep into that, because that's really not the stuff that is of importance for this course. So the concept state function is mainly important just to be able to do those thermodynamic calculations according to the Hess diagram, which are diagrams in which you go from one state to another via different pathways, and then you make thermodynamic conclusions from that. But that I will explain more in detail the next time.
Thank you. And then can you explain the internal energy?
Yeah, the internal energy of a certain system is the addition of all the possible energies that the components in the system have, and that could be kinetic energy. How fast are the particles moving? That could be due to the pressure, because P multiplied by V is also an energetic factor. Or it could be electrical. We will see in electrochemistry also that this is a possible energy. So if you multiply all of these energies, you have the internal energy of a system. So within a system, we can change energies from one to the other, but it's a zero-sum game. So that means you always have to end up with the same energy, internal energy, than what you had before. But you can, for instance, change the PV energy, the structure's energy, you can change to heat. But the total amount has to remain the same. You can change the chemical energy to heat or to pressure, You can change the electrical energy to heat or to chemical energy, something like that. Yeah. So, but the total energy always have to remain the same. That's the first law of thermodynamics within a closed system has to be. If it's not closed, of course, you can exchange energy. But as long as you have a closed system, or you have a system together with its environment, can also be considered as a closed system, then your internal energy has to remain constant. And this internal energy is the sum of all possible types of energies.
About eternal energy, are there any special cases, any kind of exception or anything worth noticing?
I'm not sure I completely understand your question. Eh?
Yeah.
So maybe you can you write it in the chat perhaps, because and formulate it a little bit better.
I think it's
Yeah.
yeah, I think my question is a bit unclear, so I think I will
Yeah.
send you when it is
Okay.
clear in my mind.
Okay. I'm very sorry, but for this session, I have more or less to finish now to be in time for my other meeting. I hope we can spend maybe a bit more time next week. I think we have probably next week another meeting, if I am correct, or in one of the next weeks. Then I think we should be able to discuss, to go a bit more deep into exercises with thermodynamics, and maybe the things will become a bit more clear then. So yeah, I think 5th of May. I think we have another session. Yeah. Okay. If you have any questions in the meantime, you can always send me an email also. No problem. Okay. So I'm sorry, but I have to leave at this moment. So I wish you all the best, and I'm looking forward to our next sessions. And of course, I'm also looking forward to meeting you in person in Vietnam. So my trip is getting planned now. So, and I'm really looking forward to visit Vietnam again after 2 years of absence, maybe even more than 2 years. I think my last visit was in January of 2020. So I'm really looking forward to seeing everybody again. Okay, so bye-bye, and I think I have to leave now. Yeah.
Bye.
Thank you,
Bye,
teacher.
Goodbye, teacher.
Bye.
Bye, Professor.
Bye, teacher. See you in Vietnam.